Okay, so I'll go ahead and write down the answer for this one in case you guys want to check. So the horizontal acceleration should have been about 4.79 meters per second squared, and the vertical component of the acceleration should have been about 7.59 meters per second squared. Okay, so if you got that part right, feel free to jump ahead a couple minutes. If you didn't, no fear, right? We'll work through this and set this up. Okay, so question kind of a little bit confusing, and maybe the one thing that they should have clearly stated for us that they didn't is we will assume that the craft has a constant acceleration in both the x and y direction and overall acceleration as well. I feel like this question probably should have stated that because that is a big tip-off. If we know it's a constant acceleration, we know that we can use our kinematics equations, and that becomes our goal. Right? If I want to set up a function for the craft's acceleration, then if I know I have kinematics, I can just start identifying what information I have. Well, I have the time, right? It tells me the period of time, and it gives me the initial x velocity, the initial y velocity, and it gives me the displacement for each the x and the y that it went during that time. So again, the second, if they had told me that this was a constant acceleration, the second I see that, then I can just jump in with good old kinematics, right, and work from here. Okay, so anyway, plugging in my displacement for the horizontal measurements, I've got 4.11 times 10 to the 6th. I again know my initial horizontal velocity is 4,370 times the time of 684 seconds. So obviously, yes, these numbers will get very large. Just careful calculating it, right? And then 684 squared, again, going to get very large here. Okay, so at this point, it's just algebra, and I know and trust that you guys can do some algebra. So when you solve for this component, that's again where you get the 4.79 meters per second squared. Okay, so if you didn't, just check all of your math. Make sure you subtracted this over first, and then divided by whatever you got from 1/2 times 684 squared. So if you didn't get this number, just double check your work. And then do the same type of thing for your vertical acceleration, right? So delta y equals the initial vertical velocity times time plus 1/2 at squared as well. Okay, so again, I've got all of those measurements to work with. So 6.07 times 10 to the 6th equals my 6,280 times still using 684 because it's still accelerated for that long vertically, right? If it did it horizontally, it did the same length of time vertically. And once again, solving for that vertical acceleration, that's where I got my 7.59 meters per second squared. Okay, so those are the two components, and they don't even ask me to find the resultant. They just ask me to find the x and y components of the acceleration. So at this point, I've set up my functions, and then I've solved them from there. Okay, so hopefully this wasn't too bad, particularly once we realize that it is supposed to be a constant or an average acceleration. And then the last question, you'll notice I actually did have a mistake on this one. It should have said find the direction of the average acceleration. To actually find the average acceleration, we would be missing information because we know acceleration is change in velocity over time, and obviously I don't give you any instance of time, nor do I give you specific velocity vectors that you can work with, right? Okay, so this is more about understanding again the direction, which was the piece we looked at in class. Okay, so I'm just going to mirror these two here real quick so that I can then move those around as I need to. Okay, so if I want to find the direction of the average acceleration, again, the way that we do that, and this is the process, this is really the only point of this question that I want you to be comfortable with, is I take my second vector, I take my ladder vector here, and then I subtract the first one from it, and that will show me the change of velocity, right? And we know that the acceleration vector is going to be in the same direction as the change in velocity. That's what this equation really shows me. So then all I have to do is I take my second, or I can just move the whole picture, I guess, but I'll try not to do that. I take my second vector, and then I subtract the first vector from it. So in order to subtract the vector, right, that's where I add the opposite. So I reverse the direction of that, and then I add that to it. So starting at the head of the first, or the second vector, excuse me, I'm going to place the first one, right? So then the resultant of these two, which would be the change in velocity, the resultant of these two vectors would look something more or less like this, right? And that would represent my change in velocity. However, there is one thing you have to be careful about. We know that the acceleration vector will be in the same direction as the velocity vector, but it will not necessarily be the same length. Okay, so as I throw my acceleration vector up here, I have to realize that I actually don't know how long this vector is. Now I know that it points that same direction, which is what I was asking you with this question, but I don't know how long it is because, again, I don't know what frame of time we're looking at. If we're looking at a really short period of time, then that acceleration would be much longer, because if you divide by a very, very small number, right, that acceleration is going to be big. However, if I'm looking at this happening over a long period of time, then that acceleration might be a fairly short vector. Okay? The only thing I know for sure is the directions of those two, the change in velocity and the acceleration, have to be the same. So do be careful about that one. And anyway, hopefully that answers any questions you might have had here on question 8. Again, I made the mistake of not including the direction, so I hope that didn't cause you guys too much concern initially.